So now it's time for next project. And this is the autonomous bike. I leave the word to Victor.
Hello, hello. And welcome to the presentation for AutoBike. I'm Victor, and I'm the project manager for AutoBike. This is my team.
I'm Love. I'm the requirements manager, and I'm the requirements manager, and I'm part of the hardware team.
I'm Gabriel Sharif. I'm safety manager, and I'm a hardware member team.
And I'm Maya, and I'm the verification and validation manager and a member of the software team.
Yes, and also on AutoBike is also a collaboration with Chalmers University. So both of us are developing this project together. We also have a few sponsors in the industry: Veoneer, Autoliv, Volvo Cars, AstraZero, and Cycle Europe. Here you can see some content that we're gonna present. So first we're gonna do a background, some requirements, an overview of the system, then how we have tested the system, and the safety, and then finally the challenges and the future work. Yes. So what is AutoBike? AutoBike is an autonomous bicycle that's supposed to simulate how a human drives. This is so we can train and validate the crash avoidance algorithms from Volvo Cars, autonomous cars, to help the safety of the future. That's the overall goal of AutoBike. This has also been a project throughout the years. So from the earlier years in MDH and Chalmers, they have also created different concept bicycles, where MDH have mainly focused on LabVIEW, and Chalmers have focused a lot on Python. And our task is to combine these best aspects into a solution. Yeah, so our goal for this is to make the AutoBike more dependable and more reliable. We're going to achieve this by making it more accurate, and so we get sensor data more accurately inputted, and the calculation is faster. And we're going to do this by evaluating the hardware that we got from Chalmers, and also evaluate the software that we got from them, and also recreate a new software in the LabVIEW real time that is more reliable and faster calculations.
So in this project, we worked a bit with requirements to help us guide us in our design solutions. And first of all, we started with meetings with our stakeholder, Jonas from Chalmers, to figure out his needs and his goals. And then we followed an iterative process where we took these higher level requirements or goals. So for the first iteration, it would be the stakeholder goals. And then with the help of different models for different iterations. But for the first one, it would be a use case diagram to properly elicit lower level diagrams. So for the first iteration, that would be the stakeholder requirements. And then we will go deeper and deeper into the system. And following that would be a verification effort to figure out if we actually had done what we thought we had done. And if that effort would pass, then everything is fine. But if it would fail, then we would have to redefine the system until it would pass the verification.
Okay, here is hardware before. This is an old picture. We took it the first day. There you can see circuit with a lot of cables. If you think about the AMC is going to make some issue. But here, a motor control located on the cover and a battery in the middle of the box are not included in this picture.
And this is a picture of the new hardware. So it's the same box as before, and none of the components, as Gabriel mentioned, that were absent in the last picture, they are included here as well. But the main takeaway here is that it's a lot less wires, so it will probably cause less issues with the EMC. And then you can also see that we have a lot of spare space in here, so we can add other functionalities if we desire to. We received smaller boxes from Chalmers. However, those were slightly too small for the batteries to fit at all. So we decided to use the old box instead of destroying the smaller boxes. That's why we have the excess space. And then we have this circuit board acts as an input-output for the MyRio, the microcontroller of the AutoBike. And it also features power distribution capabilities. But having those two features on the same circuit board induced some problems. So we got noisy signals from the sensors and such. So we decided to move the power distribution capability to a DC-DC converter that we produced. It's located in the cardboard box on the top. Yes?
We have this. We have the same motor steering here. So this is from AutoBike.
So this is a schematic of the picture you just saw, and it also includes some of the features that are outside of the box. So for example, some of the sensors are located, the speed sensor, for example, is located on the rear wheel, and we have an angle encoder to figure out what angle the steering wheel is on. And this is a schematic of the power distribution board that we created. When we received this on the input-output circuit board that I just showed earlier, they only had the actual converter. But we followed the producers of the converter, their recommendations to feature capacitors and an inductor to reduce noise, basically. And then we also added some robustness features. So we added a fuse for overcurrent protection. We added transient voltage suppression diodes for overvoltage protection, and then we added some reverse polarity protections. And the idea of this is to have the battery power the MyRio device, and then the MyRio could itself power its peripherals. And this is what we call the finder circuit. It allows for the emergency stop button to work properly. And what you see here is basically the line from the battery transmitting power towards the motors of the AutoBike. And power will run through pin 1 and pin 2 of this finder component only when this button is pressed. And this button can also be pressed when power is flowing through the coil here. And by pushing the reset button, we allow power to flow through the coil down to ground, and this allows power to flow through the finder, and then through the e-stop button do a feedback, so it will self-sustain. So in practice, if we push the e-stop button when it is alive, we will kill it. So no power will flow through the motors. So this is as a safety measure.
In the next two slides, I will give you a brief description of the old software and the new LabVIEW code that we have created as a team. So the old software, the old bike is controlled by using a standard way, using an algorithm implemented in both LabVIEW and Python. So basically the FPGA reads all the data and then save it in the registers, then the Python will read these registers. Actually, the Python code runs a start script called easy start that sets all initial value to zeros like longitude, latitude, the speed over the ground, and etc. And then the code will calculate the needed parameters such as the travel distance, the you choose U-turn to go back to the start points and GPS position. And after that, the Python code will send a command to steer the motor. And at the end, or the last step of the code, will get a description of the experiment and recording the path of the bicycle. And here, an overview of our new lab view. We have a new executive order, semi-parallel execution. We start with checking all components, calibrate the parameters of the system. If something goes wrong, as you see at the top of the picture, we have an emergency stop to stop the system and in order to recalibrate all the system all over again. And if everything is under control, though we can go or run the code into a main control loop. There we will the code will read all the signals from the sensors through a C code that's integrated into the lab view, and then send the commands to the actuators and so on till the test is completed. Then the code will run out of the main loop in order to save data, set actuators to the default values, and to stop LabVIEW from running. And the testing of AutoBike, the mission or the main mission of the verification and validation was to conduct a continuous testing under the life cycle of the projects in order to fulfill the requirements with the different levels and of the software against the hardware functionality, the subsystems, execution, any possible users or interfaces that can interact with the system for achieve optimal end product at the end. And we have succeeded. This is a result of one test that we had achieved, and we have succeeded to achieve a faster execution time and a more reliable sensor data collection. We have total 10 milliseconds, 5 milliseconds to collect the data, and we're supposed to have 5 milliseconds to calculate the execution process. But we have succeeded to do this under approximately 2 milliseconds, as you can see on the second blue bar of the graph.
Yes, and here you can also see the accuracy of the sensors that we have measured. You can see some noise in the graphs, but that noise is usually 0.1 or 0.2, so it's very small and most likely acceptable. We just want to show the accuracy of the sensors here.
Here is risk analysis schematic. This is process for safety and risk analysis in this project. This is important to define the system as the first case. To find and discover the hazard, analyze them to see how each hazard will affect the system. There are high level of risk run over every time, like a loop. As I said, this is important to define the system, identify the source of risk, each of risk, in order to be able to estimate the severity and probability to estimate of the consequence and the probability. Those number or those estimates will give us a picture of the risk level, which we can categorize them in which level they're going to be. By estimated, a hazard can be accepted or modified. If the risk is accepted, we continue with system to following up the system and operating. If it's not, we should to modify the system to having a goal to minimizing the risk level from high level to medium. Here is some result of hazard. You can see everything is the first one is hazard, and the second one is causes and effect, and probability and severity. Probability and severity will give us some number in hazard risk index, which is a standard to find the level of risk. And here is risk decision criteria and hazard risk index matrix. So if we do have something here, some number for A1 to 4 is going to be risk decision criteria, and every risk decision criteria has the level regarding hazard. The level show how danger is the hazard. This is high level of hazard. So this is the maximum level, and it's those hazard we take care of them by recommendation and looking at the effect of recommendation. Some of them we implemented, and some of them, the first one is going to be future work by recommendation and by general proposal recommendation for safety. We did have some existing safety measure. The first one is circuit breaker, the second one is power switch, and the third one is edge stop. You can see here in the red ring, circuit breaker, and edge stop and power switch. The edge stop is emergency. If something happens in the system, we need to stop them, just push them, so everyone knows it about. And power switch is to completely shut down here. Shut down the system if we want to test only one part of system, the software part. The circuit breaker, which we have here and there. If we shut down them to make it easier to test the software without any action in the forward motor or a steering motor. So we cannot have any action when we send some command to test the Hall sensor or Myrio do the job.
Okay, now we have gone over all the aspects of the project that we have done. So now we want to highlight some of the challenges and the problems that we have had throughout the project. So first off, the main one. We discovered about halfway through that the Python code, that is the control code for the whole bike, won't work in LabVIEW real time, which is the operating system that we are using in AutoBike. This meant that the whole system have not been able to be tested fully. Only about 50 to 60% of the system have been able to test. So that will be about future work. But also another problem that has wasted some time for us is the lack of documentation from both MDH and Chalmers, where when we had to continue the work, there haven't been much documentation. So we have to reverse engineer a lot of components to be able to understand them. And this has wasted a lot of time. Also mention that it's a minor problem, but due to the pandemic, a lot of components, when we need to order them, have either not been there. So you have to search for a lot of alternatives, and also been delays in delivery. So that's also wasted a bit of time. But now, future work. So we have, in conclusion, we have implemented majority of everything that we were tasked to. So all the sensors, all the actuators are implemented, except the forward motor. That we had some problem with the UART communication, so that will be future work. Also, the control algorithms, as I mentioned, as in Python, doesn't work in LabVIEW, but we found a solution in using C code instead. So that is, we need to translate the control algorithms from Python to C code. And since we divided the power distribution and signal boards, that's also, so now you can remake the boards to reduce the size of the that needed in the box. And yeah, and also mentioned that the built-in test to validate the system during the runtime. We have a few of those, but more is always better. And also electro EMC that we mentioned, that we reduced with the new PCB design. We have done these changes, but we haven't fully tested if they are working. So that also needs to be further validated. But yeah.